Welcome to Lecture 14, Standard Scores, or what is known by Z-scores. Today we translate raw values into a universal scale, a scale that tells us how far a value sits from the mean in standard deviation units. A Z-score answers one question: how many standard deviations away from the mean is this value? The formula is very simple. It is Z equals to this value, which is X, minus its mean, mu, over the standard deviation. If the value is above the mean, Z will be positive. If it is below the mean, Z will be negative. If it is exactly at the mean, then Z is 0. Z-scores lets us compare values across different groups, different units, and different scales, all on one standardized ruler. We use Z-scores to compare performances across different populations, standardize different units, connect raw values to probabilities, and use the standard normal table to calculate these probabilities. Everything in today's lecture flows from this idea. So let's begin with a fresh example. Two runners complete a race of 10K. Runner A finishes in 48 minutes and with mean 52 and its sigma is 6, while runner B is finishing the 10K race in 55 minutes and sigma is 10 while its mean was 62, and would like to compare these two players together, which one was faster, and each one is coming from a different population. Here we do have mu equal to 52 and sigma 6, while here is a little bit higher, so slower, and sigma is 10. So let me compare them together using the Z-score. So I'm gonna calculate Z-score for runner A. Again, Z-score is the value, which is here the 48, minus the mu for this runner or for its population, which is the 52, over sigma, which is 6. And if we calculate this one, it should give me a 0.67, 2/3. While if we calculated the Z or get the standardized value for the second player, player B, it's again its value. He finishes in 55 minutes minus the mu of his population over its sigma, and this is giving us a minus 0.7. So both runners are faster than the average because it's negative for both of these ones. The standardized value is negative for both of these ones, which means their time is less than the mu. So these are faster than the average in their population, but runner B is slightly further below their group mean, so runner B performed better relative to their group. Sometimes we know the probability and want the Z-value. This is called backward reading. The steps are: sketch the area, and then ask, is this a left tail area, cumulative area? If yes, go straight to the table. If no, convert it first to a left tail area, and then find the closest area to the closest area in the table and report the associated Z. So suppose this is the area which happen to be my left area, and I'm gonna report the associated z value, which is read as we discussed before from the label of the row, and stick to it exactly the label of the column. So z here that is associated with this left area 0.67 is equal to 0.44. So let's practice. Find the z value such that the area between 0 and z is 0.1848. So the first step again is to put our area on a graph. So let we do that together. I want the area exactly between z0 and z0. That area I want it exactly to be equal to this value. Now, is this area a left area? No, it's not. I need to transform it to a left area. So to transform it to a left area, I need to come from the minus infinity of my curve to that point. So I need to come from the far left tail of my table, of my graph, till I hit the z-naught. So if this area is 0.1841 between 0 and the z-naught, the area between 0 and minus infinity underneath that curve is exactly half of the curve, and it should be 0.5, since we did say before that the total area under the curve is exactly 1. So half of it from 0 to minus infinity is half. Now my area is now equal to 0.5, which is the part I did add, plus the 0.1841, which will give me 0.6841. Now I can go ahead and take this value or this area and look for it in my table. So I need to go ahead and find the 0.6. So this is 0.65. The closest area to 0.68 would be 0.6772. So I am here 0.6808 and 0.6844. So the closest area is actually that one. My 0.6841 is closer to that value than this value, so my z would be exactly equal to 0.4, and the second decimal I'm gonna read it from here. So here is the 0.08, and I'm gonna stick it beside the 0.4, so the value would be actually equal to 0.48, and so the closest match corresponds to z-naught equal to 0.48, and this is the solution that will give me that the probability between 0 and this 0.48 is exactly 0.1841. So let's find z-naught such that the probability of z less than this z-naught is equal to this value. The first step is to put it on the graph, so let's graph it together. Now I know that half of the area under the standard normal table from 0 till either side is half, and this value is less than half, and it is a left area, left. So my Z node has to be on this negative side of my curve. Why is this? Because logically that 0.305 has to be within that half of my curve, because if Z naught was 0, then it would be half, but it is less than half, so Z naught should be less than 0. And this is good because this is a left area. This is my left area. I can enter my table safely. So let's look for our area 0.3050 in my table in the negative part, because we have said that Z would be negative, and I'm gonna just look in my values here till I find the value 0.305, and here is my value exactly here. So I'm gonna report the associated Z, which is minus 0.5, and the second decimal is that one. So this is the solution of our problem. Now, if I didn't find my area exactly in my areas here, among the areas in my table, then it would be for sure between two of these. And in this case, I'm gonna report the Z that is associated with the closest area to my target area. Sometimes, however, it would be midway between two adjacent values. In these cases, I'm gonna just take the average of the associated two Z's and report that average as the solution for my problem. So let's see this one. What is the Z node that is gonna let my probability of Z greater than it equal to this little tiny value? Now, the first step, as we said, we need to graph my area on the graph, and this is a right area, so I can go ahead and transform it to a left area. So my target originally was a left area, a right area, and it was very small, and right area, so for sure it is on the positive side of my curve. So this is my Z naught. And I cannot enter my table with this right area. I need to get the left area, so I need to calculate that one. I know that the area under the curve is 1, so this dotted area, the left area to this Z node, is equal to 1 minus, so 1 minus 0.0912, which will give me 0.9088. Okay, so this is that left area, the dotted area. So this is the dotted area. Now this is a left area, and I can safely enter my table with this left area and get the Z naught. So let's see that. So let's look for our left area, the one we calculated, 0.9088 in my table. I'm gonna look here, this is 0.5. I'm gonna just go down till I find my area, or at least a closest area to that one. This is 0.93. I need to be a little bit beneath this. This is 0.9066, and this is 0.082, and my area is exactly, if it was in my table, it should be above that area and below this area, so it's somewhere here. However, it's closest to that 0.9082, so my area, or my Z, is the one associated with the closest area, which is 1.33. Now let's connect these scores to real-world probabilities. To find the probability that X falls in a certain interval, we would draw the area, convert x to z using the z-score formula, which is z equal to x minus mean over sigma, and then use table or calculator to find the area. So let's tackle this example. Battery life is normally distributed with a mean of 18.5 and a sigma or standard deviation 1.25, and we want to find what is the probability that a battery lasts less than 19.4 hours. The first step is to go ahead and translate or convert this x to a z using our z-score. So let we do this together. So transforming that x to z, it means I need to apply the z-score formula, which is just taking your x, subtract from it the center or the mean, and divide it over sigma. If we did this, we will get a value for z, a standardized value that I can use in my table and get the associated area or probability. Read it from my table and put it as the solution of this part. So here we are just converting. So 19.4 minus the 18.5 over 1.2 sigma. This will give me exactly 75.75. So now converting that problem to a new problem, which is a probability standardized unit, z less than, here I was left, so I will keep the sign, but just change that 19.4 to my standardized value, which is that one. Now, all what we need to do is to go ahead and look for the area that is associated with this 0.75. Here is a part of my table. Here is 0.7. Let me just let you see what here is 0.7. So I'm gonna just go ahead and go to 0.05, so 0.75. This is the value. So it is that value then. This one from my table is 0.7734, which is again this value, okay, which means that about 77% of batteries will last less than 19.4 hours. So let's see this example. Daily coffee consumption is normal distributed with mu or mean equal to 14 ounce and sigma standard deviation 3. And we want to find the probability that the consumption would be between 12 and 20 ounce. So again, we need to convert this to standardized values. So let we do that together. So I will convert the 12 and the 20 and see what is this. Let me call this was x1, okay, and this is x2. So for x1, I'm gonna get the z1, which would be 12 minus 14, again the x value minus the mu over the sigma, and this would be minus 0.67, while the z2, if I'm gonna apply it on my x2, it's gonna give me 2. Now I can graph this on my table or on my graph and see that area. So this is the standard normal table. By the way, you could graph it on your X, so no, like considering the graph for X, but usually it's better to do it on your Z, the standard normal variable, or Z-score. I have here a 2, so this is my 2, the Z2, and I have minus 0.67, which is maybe closer to that one. So this is minus 0.67. And what we want to calculate, and let me just get rid of that zeros, and we know that this is my 0. Let me just put it down there. Okay. So my area here, I want to calculate that in between area. How to get it? Well, this is a result of two areas. One of them is that one. So I have two areas, and this target area is the difference between two areas. So one of them is that purple area, left to 2, and the other one is actually, let me highlight it, is this left area that is exactly below the minus 0.67. So my target area, which is the red area, is the difference between the purple one minus the yellow one. So this is what we are gonna do now. I will enter my table with the two numbers, the 2 and minus 0.67, and subtract the smaller area, the yellow one, the left to my Z1, from the bigger area, the left to the 2. So let we see what are these values. Here is part of my table, which is associated with the 2. Here is your 2, and I want 2 only, 2.00. So my area associated with that one is actually that value. This is my purple area, and the other one associated with my minus 0.67. Here is minus 0.67. Let me just use that one. Here is minus 0.67, minus 0.6, and I'm gonna go my table till I hit the column which is labeled by 0.07. So this is the value. Let me just, this is the yellow area. So all what I need to do is just subtract the smaller one from the bigger one. So this means my probability of Z between, let me write it for easy, between Z1 and Z2, where Z1 is minus 0.67 and Z2 is the 2, is exactly equal to the purple area, which is 0.9772 minus the 0.2514, and this will give me 0.7258, which means actually that about 73% of people are in that range, consuming coffee between 12 and 20 ounces per day. So a machine fills cereal boxes with mean equal to 500 and sigma equal to 12 grams. Find the probability a box weighs more than 520 grams. This is again in terms of x, we want to convert it in terms of z using our z-score, which is 520 minus 500 over 12 will give me 1.67, as we have seen how to apply this formula before. So calculating probability of x greater than that value is exactly calculating the probability of z, the standardized value of the 520 greater than 1.67. Again, I will put it on my table. This is a right tail area. So on my graph, I want to find this area. However, my table cannot give me this area directly. It will give me the left area, and then I need to subtract it from 1 to get my target area. So I'm gonna enter my table with that standard value, 1.67, and read the associated area. However, this area again is not my target area, the right area, it is the left area. I'm gonna subtract it from 1. So let me see that. Here is our table, and this is 1.6. I'm gonna go till I hit the 7th column. So this is my area, which is 9525. So my dotted area is actually that number. I don't need that number. I need the complement number. So it is 1 minus point, what was that? 9525. Okay, this will give me 0.0475. So about 5% of boxes exceed the 520 gram. So which is okay. Sometimes we want the value x that corresponds to a given probability. In these cases, we will use this formula, where I need first to get the z associated with the given probability from my table, and then using that formula, I will transform it to my x, which is following the normal distribution with the specific given mean for that x and the specific given sigma for that x. So it's like you are actually entering the problem with sigma and mu and a specific area under the curve, which you can use the table in an inverse manner to get the z associated with a given probability, and then transform it back to the original scale of your x. Let's practice. Test scores are normal distributed with mean equal to 70 points and standard deviation equal to 9. We want to find the minimum score to be in the top 5% of the distribution of the score. This is the top 5%, so this area is 0.05, and I want to find what is the value here, which is z naught, and in the same time it is actually your x naught, so the score you want. If you are looking at it in terms of standardized units, it's z naught, and this is what we are gonna get from the table when we want to get the z naught associated with this 0.05 from my table, and then using our formula to transform it back to the x naught. So let we see what is the value associated with this 5%. So here is part of my table, but hey, wait, this is what? This is a right tail area. I need to enter my table with a left tail area. So this dotted area is the one that I need to enter my table with, which is nothing but 1 minus 0.05, so it is 0.95. So this is a 9. So I'm gonna enter my table using that value, searching my table here for 0.95. I am close here. Here is 0.9505, and this is way above the 0.9. So if my 0.95 was in the table, it should be between these two values, and exactly, not only that, exactly in the middle. Because of this, I'm gonna just report that Z naught as the average of the Z's that are associated with these two values, the 1.64 and the 1.65. Getting the average of these two will make my Z naught equal to 1.645, just exactly in the middle between these two. Okay, between these two. Now this is our Z naught, and I want the score itself, so I need to transform it back to its original scale, which is mu plus Z naught sigma. So I'm gonna plug here my 70 plus the 1Z that I got from my table, multiplied it by the 9, the standard deviation units, and this should give me 84.8, which is almost 85. So 85, I need to get 85 to be in the top 5% of the distribution of this score. So plant heights are normal with mu equal to 22 centimeter, sigma equal to 4 centimeter, and we want to find the middle 50 range. The middle 50 range is gonna be bounded with 2 bounds. The lower one is the lower 25%, and the upper one is the upper 25%. To be exactly in the middle 50, it means I need to get from the area under the curve 2 pieces, which is the lower 25% and the upper 25%. If I'm gonna get rid of these two tiny tails, then my target area would be exactly the middle 50. So I want to find this Z1, let me call it Z1, and Z2, and when I'm gonna transform it back to the original scale of the plant heights, it's gonna be X1 and X2. So now I do have two areas. I need to enter my table to get the associated Z1 and Z2 with each one of these. But again, my area in the table should be left. So with Z1, I'm gonna enter my table with this, with this yellow part, and I can enter for the Z2, I can enter with that whole, with that whole one, purple one. However, from symmetry of the distribution of the standard normal and the normal in general, if this is 25 and this is 25, so I am gonna just read one of them, either the lower one or the upper one, and give the other one the opposite sign. This stems from the symmetry of the curve. So now I'm gonna enter and check for that table. Here I do have which one. I used here the negative part, so I'm gonna enter with the 0.25 area. Let me, 0.25 area. And here is the 0.25 area. It is 0.26, 2611, 2578, 254825. So it is between, if it is in my table, it should be between these two numbers, but it is more close to that number, which is 0.2514. So I am gonna report Z as minus 0.67. So let me write it here. My Z, okay, let me pick another color for that one. Z1 is, this is, I have a minus here, so it's minus 0.6. And I'm hitting the 7th column, so intersection between the 7 columns and the minus 0.6 row, it will give me that one, which means from symmetry, Z2, why symmetry here plays a role? Because I have the same area below and above, so this is symmetry, will give you 6, 7, but with a positive sign, and this is from symmetry, which means I can calculate my x now, x1 and x2. So x1 would be mu, which is 22, applying the formula again, plus z1. Z1 is negative, so I need to put the negative sign here, times the sigma, which is 4. So it's 22 minus 4 times 0.67, and this will give me 19.3 centimeter, while x2 is exactly the same, but the sign of the z is positive. So it's gonna exceed my 22, of course. And this is multiplied by the 4, and this will give me 24.7. So the middle 50% of plants fall between 19.3 centimeter and 24.7 centimeter. Lifetime of light bulbs are normal with mean 900 hours and sigma 120 hours. A company wants no more than 8% of bulbs to fail under warranty, which means the bottom 8% of the distribution of its production of those bulbs. So no more than this one to fall under the warranty. So this is unknown, and we want to know what is that Z naught. So that Z naught is how much? This is actually inverse reading from the table again. So let we look at our table. This is a lift area. This is lift area. So I can enter with that 8% in my table safely. And here is 0.0808 and 0.0793. My 0.8 is not in my table, but it is between these two numbers, but closest to that one. 0.808 is closer to that one than this one. So I'm gonna report my Z naught as minus 1.41. Being closer to the 8%, this means my X naught, or the lifetime in terms of its original scale, in terms of hours, would be 900 minus, just because I do have here a minus, or I can just write it in its normal rule, which is plus the Z naught times the 120 and this minus and the plus will transfer to a minus. This will give me 73.1.8, which is roughly 732, of course, hours. So the warranty should cover 73 hours only, so that it will have only 8% covered by the warranty. 8% of the distribution or of the production of this company. So today we learned how these scores standardize values. Also, we did see how to convert x to z and z to x in many examples. Also, we learned how we can find probabilities using the standard normal table. As for the calculator, we did not use the calculator in our lecture. However, you can see how to do it. If you see or watch episode 6, I'm gonna leave a link for it in our lecture. Episode 6 for the TI-84 series with dot. You will see how to use the calculator or apply whatever we did discuss today in the TI calculator. Also, we did see how we can solve real-world problems using the normal model. And actually, this is the foundation for everything that follows in probability and inference, as we will see in our course. This is the end of lecture 14, standard scores and normal applications. Thank you for being here. And as I said, we are gonna use what we have learned today heavily in our remaining parts of this course. So thank you and see you in our coming lecture 15.